Thank you for coming.
Thank you.
I will please ask you to give a big clap to Ami and all the organizers for making the conference available.
Thank you. Thank you.
Okay, so we're going to talk a bit today about memory exploitation. Well, I mean, exploitation of memory corruption bugs. I'm pretty sure you guys know a bunch of them, like stack overflows, heap overflows, etc. What happens is that it's massively not scalable. When you're trying to exploit vulnerabilities, the amount of reverse engineering involved nowadays, because of protections, etc., gets so huge that there is a need for automation. It's not about saying that it's easy, cheesy work and that we should automate at all costs. But honestly, when you're trying to attack, say, a web browser and you get a memory corruption, the mapping of the memory is so huge that you can just not do it manually, right? If we try to single step into a web browser like Firefox, given the size of the application, we're pretty sure it's not possible. So this is where there is a need for automation and having new approaches to exploitation. Instead of trying to automate what we would do manually, we're going to try to find new ways, entirely new ways, to debug applications. Another thing to take in mind is that most debuggers today under Unix are basically ptrace based, and the only one which is decent is actually GDB and all its front end and stuff, but it's pretty much the only one which actually scales to big applications. If you go for other types of debuggers like the one from RELRO, they work nicely on small binaries, but they don't scale to big applications. So the problem with GDB is that it's been built thinking about fixing software. And honestly, I'm not too interested in fixing software. What I want is to break software. So there is a need for a new kind of mindset and new kind of tools. If you have any questions at any time, feel free to ask. So who am I? Ami gave you a nice and long introduction. So basically, I think the whole story that I have a passion in life for reverse engineering, and I managed to have that as a full-time job, so I'm pretty happy with it. What I don't like do is everything which is cheesy, like reversing plain text or web application and stuff. I'm not a great fan of that. Honestly, it's like a given. If it's all in plain text, there isn't much to check. To the opposite, if you're attacking binaries, it can get so complex that that's starting to be interesting. Okay, I'll start with a few basics on exploitation. If you are already writing exploits and familiar with modern exploitation, that's going to be super boring to you. So let's have a deal. If it gets boring, you just raise your hand and I'll go to the next slide. I'll explain you why it's important for a debugger to be environment aware. And we'll see the tool I'm introducing today, PMCMA. That's a lot of M. I'll explain you a bit of the design and how we can extend the tool. By the way, tomorrow there is a Hackaday session, and we'll try to port PMCMA to other architectures. So far it's working on Android and Linux, on Intel architecture, both 86 and 64-bit, 32 and 64-bit architectures. Tomorrow we'll try to port it to BSD and hopefully OS X. Okay, so PMCMA, this tool we're talking about, it's also a ptrace-based debugger. So its goal is to help you automate exploitation. It's not yet giving you full exploits, neither in binary or source code format or whatever. What it does currently is really automating some really difficult checks that you could not do manually and help you find a way to exploit the software. So the output of the tool is exploitation scenarios. So there are different kind of memory corruption bugs. We mentioned like stack overflows, missing format strings, things like that. part of PMCMA, the first analysis it does is trying to understand when you can trigger a bug, what kind of error is actually happening. So if you're familiar with Microsoft, they have a tool like that called Bang Exploitable. So the first analysis performed by PMCMA is actually to try to understand that. It can get pretty complicated. So let me show you a demo. So we are on the same page and we understand what the tool does, and then I will explain you the internals of the tool and how to use it. So for that one, I'm going to be lazy. I'm going to use a video. I promise it's the last video. No, there are 2 videos. Okay. So let's say we want to work with beansu. Or sudo. Okay, what I did here is start sudo. I stopped it. And let's imagine that right now I can trigger a bug inside sudo by providing a very lengthy input or you know, like %n or something. Anyway, I get it to crash in some way. So I'm copying the PID of the running process, which is now in the background, and I start PMCMA by giving the PID of this application as a parameter, and it's going to start the whole analysis for me. So then you can see it's doing a bunch of analysis. Okay, the idea that in particular is going to find me all the function pointers actually dereferenced inside the application. So the tool is not finding bugs for you. What is this? Ah, laser. Cool. So what the tool does is not finding bugs for you. It's like once you already have a bug, it's going to help you exploit it. Right? The tool is available for free under the Apache 2.0 license, so it's totally open source at this address. It serves as a good framework for to include new checks, so I totally encourage you to hack it, fork it, include your own checks, and if you're happy with the result, feel free to send us the patches. There is a copy on GitHub also, so people have already started to tune it. We released it on September 1st. And in a month, we got like 10,000 downloads, which is not too bad for a reverse engineering tool. I didn't even know there were like 10,000 exploit writers on Earth, so we were pretty happy with it. Okay, let's start with a few basics for those not familiar with modern memory exploitation. So, applications crash, meaning that they receive either a segmentation fault, which is an invalid memory access of some type, or they can get a signal 6. This happens, for instance, if you have a double free, your application is going to receive a signal abort, right? So that's a different kind of memory corruption. And obviously, I mean, the first one maybe which comes to mind is stack overflows. Nowadays, stack overflows get detected by the system, so it's pretty obvious when you get a stack overflow because of the stack smashing protection implemented in GCC. Regarding the different kind of invalid memory access you can have, basically either you try to read a page or a memory address which is not readable, and this gives you an error, or you try to write to memory which is not mapped as writable, or you try to execute a page which is not executable. It seems pretty simple, but it did not used to be like that. All the memory used to be executable, for instance. Everything mapped used to be executable before the introduction of the NX bit by Intel, or equivalent software memory protection like PAX, protection against execution. So why do memory corruption bugs happen at all? Well, it can be any kind of miscomputation, really. It can be like integer overflows because of wraparound or casting errors, or changing the sign of operands, uninitialized memory, variable misuse. This is especially hard to detect. There were a few cool examples of those recently. Heap overflows, missing format string, overflows in any writable section, being in the heap, the data, the BSS, or whatever. And stack overflows, well, there is a special case if stack cookies are present from an exploitation perspective. So far, so good? So, if you have an invalid memory access in execution mode, so for instance, you have a call EAX, EAX being a register, so it's like a variable inside the CPU, if you will. If you manage to somehow trigger a bug and your application dies in an instruction like that, it means that somehow you do control EAX. Either the software never works, or it dies on an instruction like that because you do control EAX. If you do control EAX, in this case, fully, then there isn't much to do. You just win, because you redirect EAX to executable shellcode, and that's it. There isn't much to do, right? So that's a cheesy case. It does not happen much, honestly, under Linux at least. Then, if you have an arbitrary read, okay, usually in assembly, Intel assembly at least, you have the instruction first, then the destination operand, and then the source operand. The point is, this is supposed to be a destination, and if it was anything but compare, so for instance, if it was a mov EBX plus 8, 9, that would be a write operation, correct? But in this case, because it's a compare operation, this is actually not writing anywhere. It's just comparing the content of the memory at this location with 9. This is interesting because it means that if we want to automate the process of understanding if it's a write or a read, we need to know a lot about the instructions that can be used with Intel CPUs. Unfortunately, there are literally thousands of them nowadays. So there is a challenge in trying to understand automatically, when we get a crash, what's actually happening, and is it a read or a write. Another example. So this is a bug I found earlier this year in T1lib, which is actually the reader I'm using here to read this PDF is called XPDF. It's a pretty popular one. It's not the default one on Ubuntu, but it is on BlackBerry Torch and stuff like that. And I found this vulnerability in this particular reader. And actually the vulnerability is in T1lib. The application crashes on this instruction. This is even worse. Who's familiar with FLD? Well, I was not. I had to go back to the Intel manual to understand what it does. Basically, it's a floating point operation. This is very much a read. It's actually reading a keyword, so 8 bytes, and putting them into floating point register, reading the memory from this location. So if you get a crash at an instruction like that, you surely somehow control EAX. Or the code just plain never works, which can happen. All good so far? Okay. So, question is, how do you exploit invalid memory reads? Honestly, it's tough. Most of the time it doesn't work. If you can read, if you have an instruction which just reads memory into a register, the best you can do is like do a controlled read and have the register worth any value you want. Is that any good from an exploitation point of view? Not really. It depends on the few instructions which come after. Say you can read anything into EAX. If the next instruction is a call EAX, yeah, that's going to be exploitable. But most of the time, it's just plain not exploitable because it does not allow you to modify memory directly. That being said, in some cases, if you can read anything into EAX, and then EAX is used to do a mem copy of something, and EAX is actually the size of the mem copy, then you can trigger a secondary bug, like an overflow in another section. So they can actually be used sometime to trigger other bugs indirectly. Okay, now, invalid memory writes. So this is a write because the brackets here are actually on the size of the destination operand. So this is like dereferencing a pointer in write mode, if you will, if you're familiar with C. So basically what this operation does is writing the content of EAX to the memory location pointed here. This is a bug we found in Opera earlier this year. I'll give you a demo if you want. What's interesting, and this was actually one of the reasons to start working on PMCMA, is if you work with a web browser like Opera, the mapping in memory, so you have like tens of megabytes of application, and then you have like hundreds of megabytes of heap. So parsing that and reverse engineering manually hundreds of megabytes is just plain not doable. So exploiting invalid memory writes, your chances of actually managing to do something interesting are much higher. If we get back to the previous slide, here, if you completely control EAX, so the value being written, and either EBX or EDX, then you can write a quantity of 32-bit arbitrary to any memory location. So I can write stuff anywhere I want into the process. In the case of Opera, actually, EAX was null, always. So I could write 0 anywhere I want in memory. Do you think that's exploitable? Truth is, it's tough to say. Without further check, it's really hard to say. If we had full control of both EAX and one of those registers, because of the wraparound, we don't need to actually control both. Writing arbitrary memory writing any content to arbitrary memory location, this is exactly as good as a missing format string. So you could overwrite, like, say, a function pointer, and have this function pointer point to your shellcode, and then you win. So yeah, function pointers are nice targets because they allow you to transform an arbitrary write into an arbitrary execute. Okay, let's look a bit at the state of the art of exploitation. So basically, the state of the art, if you look all the papers on missing format strings and things like that, is to try to attack the detours section, which contains the destructors. If you manage to write to the detours section, which is normally writable, then you get, when the application is going to exit, the ability to execute any code you want. Overwriting an entry in the global offset table, say you overwrite the entry of printf, and you make it point to your own code. Next time the application is going to try to call printf, it's actually going to call your own code. So there used to be ways to trivially get code execution out of an arbitrary write. That being said, nowadays, the GOT can be made static, which means the dynamic linker actually performs all the relocation at load time, and then the global offset table is remapped as read-only, so you cannot write to it anymore. This is pretty standard. It's done at compilation time by specifying -t, RELRO, -z, bind now. If you take Ubuntu, for instance, it does some kind of GOT, it features static GOT for all the major applications. This has a cost, so it's a trade-off between security and performance. Regarding the detour section, if you use a custom link script, you can actually put your detour section between two read-only sections. And in this case, the whole segment is going to be read-only, which means that your detour section, while still existing in theory, will actually not be writable. So this also mitigates those scenarios. So there again, function pointers still become attractive because there is no way to make function pointers static. The whole point of a function pointer is to be able to modify it. In certain languages like C++, function pointers are actually very common. Like all the class methods and stuff are actually function pointers. All right. So before showing you how to list all the function pointers inside an application, I will explain you why it's important for a debugger to be environment aware. So depending on your target, like the version of the kernel you're attacking, like the exact implementation of ASLR, the hardware even you're using, security countermeasures may vary. You may have randomization or not. You may have non-executable or not. You may have like stack cookies. It depends on the exact version of your compiler and which binary you're actually attacking. So to take all those security measures into account, you need your debugger to be able to understand them all. The good old days of, all the map memory is executable and there are no memory protection is pretty much over. So ASLR, it's randomization. It's the fact of, randomizing the base address of libraries and potentially even the main executable. That's a big problem for replicability. If you have an exploit which has to brute force the address of a library, given the size of the address space, which is potentially 4 gigabytes with 32-bit architecture, you usually lose. That being said, ASLR is not perfect. If you're using Fedora, for instance, it's using a feature which is called prelinking, which allows to load the libraries faster by assigning them a fixed address. I think OS X also has prelinking. This totally breaks ASLR. It means under Fedora, if you execute the same application twice, it will have exactly the same mapping. And the mapping lasts for 2 weeks. They're changing the mapping every 2 weeks. You may think it's acceptable in some situation, and because it's bringing you this performance increase. That being said, from pure security point of view, this totally sucks. 2 weeks is a lot. If I'm attacking your SSH server, and I have, say, format string bug, I can easily leak the address space by using %x something, and then attack your application again, and it won't change between in 5 minutes or whatever, since it's only changing every 2 weeks. So in certain cases, prelinking is really a problem. Several kernels also had some randomization issues. I saw, for instance, old kernels mapping the libc 10% of the time at the same address. So it means if you have to do brute forcing, instead of trying to guess an address in an address space of potentially gigabytes, you can have an exploit which is going to work 10% of the time. So depending on the situation, it may be acceptable. There again, if it's SSH, it just means that you're going to try your exploit 10 times and you win. If you're attacking a web browser or something like that, and you're doing an APT, so you send like 10 exploits in the wild to people via email or whatever, and you're gonna own, statically speaking, 10% of your targets. Binaries can be compiled as position-independent executables. If they are not position-independent executable, the main binary, and I really mean like the 3 segments, the read-only segment, the writable segment and the executable segment are in static locations. It means in particular that you can find like ROP gadgets and stuff like that at static locations. So bottom line is we need to tell that all inside your debugger because it depends on both the application you're attacking and the environment you're using. So how do we test ASLR? The idea is like I take the binary I'm attacking, I'm running it a great number of times, and I check the location of each library and each section. We record this mapping, and it gives us an idea of what is the most probable address for each of the sections, and with which probability. So let's have a demo on this. Which application do you guys want me to test? Something cool. Let's do SSH. Okay, so I'm gonna create a new TCP connection to my SSH server. It doesn't have to be an SSH client, as long as I do a full 3 handshake with the SSH daemon. Is going to fork in memory and create me a new instance, and I need the PID of that stuff to be able to start the analysis. Here we go. So I should have a new PID somewhere. Yeah, there one. Okay. I need to be root because SSH runs with special privileges. Here we go. So all the analysis is automated. I'm going to suspend it for a while. So what does it tell me? Okay, so I have the PID, the command line. That's all fine. Instruction where it stopped. So registers, okay. What started to be interesting regarding the ASLR is for each library which is mapped, it tells me like what is the most probable address of mapping and what is the probability. So 2% is not too good. I mean, if we want to do a reliable exploit, if my chances of finding an address, this library at this address is less than 2%, it's not too good. Is that expected from SSH? Yeah, obviously it's compiled as a position independent executable, etc. So everything is supposed to be super randomized, and I'm running the latest kernel from Ubuntu, which is decent. So in this case, every library will actually have a pretty high randomization. Let's do it with binsu or binsudo to compare. So if I do sudo of anything, I stop the execution and look a bit at, so I need the process ID. All right. If I look at the ASLR properties, some sections are actually not randomized at all. Okay, some are heavily randomized, and some are not randomized at all. In particular, sudo is not compiled with position as position independent executable. So the three main sections of the binary sudo, okay, one is going to be executable, one writable, and one read-only. They have a probability of being at the same address of 100%. So if I have to write an exploit, and I actually use these sections, the replicability of the environment is going to be very high. Okay, let's keep on executing. So then, what the debugger does is look at all the writable sections, because by definition, a function pointer is a variable located in a writable section and pointing to executable code. So what we can do is parse all those writable sections, look at the values which could be function pointers because they point to a value which is matching an executable zone. And then what the application does, what PMCMA does, is actually forcing the debugged process to fork a great number of times. So normally you have a debugger like GDB, and it's attached to another process, like sudo in this case. Okay? You can modify the memory, etc., but you can only do it once. What we do here is PMCMA actually takes the debugged process and it injects a small shellcode inside it. I'm a debugger, so I can do whatever I want using ptrace. I force it to replicate a great number of times, like 3,000 times, and in each of the forked process, I overwrite a different location in memory, and I keep execution. I'm not overwriting with random data, I'm overwriting with a known value, for instance, F1, F2, F3, F4, which is a good pick because it's never going to be a correct userland address. It's always going to point in the kernel. So if the application then tries to execute memory location F1, F2, F3, F4 sometime during the flow of execution, you know that you just found a function pointer. So here, I have it gives me a list. The net output of the tool is like, it's giving me a list of the function pointers it has found and the repeatability, okay? So if I had to choose a function pointer to overwrite, this one is actually a very good address. If I have an invalid memory write, I just choose to overwrite this stuff and make it point to my shellcode, assuming that I can somehow make my shellcode executable. And that's game over. Any questions? Okay, so I'm going to speak a bit about the design. I give you an idea of how it works. Let's go a bit in depth, because it's not that easy to create a debugger with those features. Okay, so we're focusing mostly, at least for the time being inside the tool, with invalid memory writes. Like we said, if you have an invalid memory exec, it's pretty easy to exploit. If you have an invalid memory write, it's doable, but it's not that easy. And if you have an invalid memory read, most of the time it's bang not exploitable. One thing important is we want to scale to big applications like web browsers, SSH, things like that. We don't want a tool which just works on foobar.c. So the main idea is to use this routine which is called make fork, which like I explained to you is waiting for a segmentation fault inside an application, clears the signals, so it pretends that nothing bad happened. And then it's gonna force the debug process to replicate itself in memory, which allows us to then have easy manipulation of the debug processes. So the good side of proceeding that way, instead of restarting the process every time, is that, in particular, the randomization properties in the debugged process, because it's just forking and not calling execve, are going to be exactly the same. So all the processes are exact replicas. They are like clones of each other. Well, clones mean something in Linux, but they are like exact replicas, one of each other. So how do we force a process to fork? The idea is like we need to find a location which is executable and put some shellcode over there. If we put the shellcode in a region which is not executable, the application is going to fail anyway. So we save the registers. We use ptrace to write our own shellcode in the memory location we spotted. We modify EIP, so the instruction pointer, to point to the newly introduced shellcode. We execute this shellcode. We wait for the process to get back to the debugger. And then, after calling fork, and then we restore the bytes we have overwritten in the writable location and restore the registers. So like, we have forced the process to create a replication of itself, but if you look at the mapping before and the mapping after, they are exactly the same. Okay? So we're not modifying or introducing any bias by proceeding this way. Unlike if we had like called malloc or mmap or whatever to create a new section. So here is a typical forking process. This one is not using zeros, but honestly, I don't care. I'm copying it with a debugger and not injecting it through a, copy string or whatever. So the shellcode it does not actually need to be null byte free in this case. So we had the first debug process, and now we have a copy of it. Okay, so original process, and I can make as many copies as I want. Then the idea is like, in all the writable sections, I'm going to overwrite with a canary value, like F1, F2, F3, F4. So in the first process, in the first offspring, I'm going to overwrite the first writable location. In the second one, I'm going to overwrite a second location, etc., etc., etc. Typically, even if you have a very big heap, which is the biggest writable section usually, like a web browser, you will have maybe like hundreds of megabytes of heap, out of which only a few bytes will actually point to valid executable sections. So you will have maybe like 10,000 possible function pointers, which means you need to create 10,000 processes. And that's like doable in real life. So the good thing is it's fast and efficient. The small problem, if we do that, the main process is not aware that it created copies of itself in memory. And while those copies are going to die, they're going to create zombies, because the main process will not listen or wait for the sick child signal emitted by those processes. So if we want something scalable and being able to execute thousands or even millions of offsprings, we need to deal with the zombies. So this is done by actually injecting, so there is a trick. Okay, there is a trick with basically, if you tell the main application not to wait for child signals, you're solving half of the problem. The rest of the problem is like, we need to kill the processes we have created after some time, to make sure that we're not creating like, we keep the number of running processes at a given time pretty low. So we need to inject a small shellcode with SIG-action. The processing is pretty much the same. The only thing we change is that we're not going to inject a forking shellcode anymore, but a simple call to SIG-action. So the shellcode should look something like this. You can see that it has some zeros. There again, we're copying via ptrace, so we don't care. Okay, there is another trick involved, which is process grouping. which allows you basically to, it's a feature of Linux. It allows you to kill a group of processes who are the children of a given process. So, okay, whatever. We're using that too to keep the thing efficient. Now, one thing to bear in mind: if we create processes, imagine we are attacking SSH. At the moment, I'm attaching my debugger to SSH. All the network connection, inter-process communication, etc. are correct. But if I force it to fork 10,000 times, in the first process I'm gonna keep execution. Okay, the network connections like TCP sequence, etc. are gonna be correct. But once this application dies, it's gonna close all the sockets, etc. And in the second offspring process I'm gonna debug, it means that all the network communication, all the inter-process communication is gonna be wrong. Okay, so we need to keep that in mind. There are basically two ways to deal with this. The first way is to say, we don't care, which is, in most cases, actually correct. The other way to deal with it is to fake the syscalls inside each of the processes. So inside the first one, we can record all the processes, like network connections. Say, the application is supposed to receive a packet after you debugging it. You record the data which is received by the application, and when another offspring is actually trying to do a receive, you send him the data you recorded in the previous one. This is a bit overkill. You don't need to do that much usually. This is like a minimum virtualization thing. In the sense, what you are emulating is actually the kernel. So, what PMCMA is capable of doing so far? It's able to tell you when you have an invalid memory write. It's capable of enumerating all the function pointers. If you think about it, the current state of the art is to do this statically. If you look at tools like mona.py from Corlan, it does it statically, so it gives you a list of potential function pointers. But all the function pointers inside an application are not going to be called given a given input. So being capable of listing exactly which one are going to be called is actually super cool. And PMCMA does this not only inside the main application, but also in the shared libraries. So anything inside the process. It means, for instance, if you have internal libc call, like @exit, which uses global data inside shared libraries to dereference a function pointer, you're going to leave them too. Okay, so the way to do this is we look at all the writable memory, we look for possible pointers to other executable sections, because that's the definition of a function pointer. Optionally, we can try to disassemble the address in the executable section and check if it looks like a proper function prologue. Thing is, all the functions inside the libc, for instance, do not start with a standard prologue. So this heuristic is time-saving, but you're going to face negatives if you do so. Then we use the make-fork primitive to create as many children as we found potential function pointers statically. And we sequentially modify only 4 bytes in each of the offspring processes with this address. There again, I'm using this address because if you ever try to call this from user land, whatever is your kernel split, this is going to be in kernel land, clearly. Normally, if you have like 3 gigabit, 1 gigabit split, which is standard, is going to start at C00000. Some operating systems actually choose to have a 2 gigabit split between the userland and kernel. but I never saw any kernel starting after F something. And then we monitor the execution of each of the offsprings, and if they try to execute something like this, so if they are trying to call exactly address F1, F2, F3, F4, we found exactly a function pointer. If it's trying to execute F1, F2, FF, for instance, it may be a base address plus an offset, but we still win. Like by modifying a bit the address we're gonna use to overwrite, we can make it point to arbitrary location inside memory. Yeah, I'll make you another demo later. Okay, so among all the bugs that do exist, in an ideal world, if you have like a mov somewhere EAX, like we had with the opera thing, and you actually control both operands, you can write anything anywhere. That's back to the case of missing format strings. In this case, it's usually a game over because you can redirect the flow of execution anywhere you want. But sometimes you don't have that much control. So we're going to check out how to extend PMCMA to check other kinds of scenarios where you have less control over the operands. Okay, PMCMA can also check for overflows in any writable section. Basically, it's currently listing you all the function pointers in all the writable sections. If you have a heap overflow, for instance, or a BSS overflow, you just limit the output of PMCMA to the BSS section or the heap section. That's it. But it means that it can help you automate not only the exploitation of atomic invalid writes, but also whole section overflows. Okay, so like in the case of the opera bug, where I could only write 0 to memory, sometimes you don't have full control. So being able to write only 0 is like an extreme case. Sometimes you can choose a few values. How do you determine is this can be exploitable? Well, the idea is, for instance, to try to truncate. If you cannot overwrite completely a function pointer, maybe you can truncate this function pointer. So PMCMA is also capable of telling you, okay, I found a function pointer at a given address, and I can overwrite only with 41, 42, 43, 34. So it's going to try to tell you, okay, I found a function pointer here, and if you truncate it, it will become something like this, which actually points to mapped memory, which is, in this case, readable, writable. Okay? I wrote this tool because basically I really wanted to exploit this opera bug where I could only write zeros. And the write was also 4-byte aligned, which means I could not truncate a function pointer. Function pointers are usually 4-byte aligned. The compiler makes them 4-byte aligned for performance reasons. So I could make any function pointer I wanted 0, but 0 is not executable. Since kernel 2.6.23, you can actually be sure it's not going to be executable because it's a memory protection to prevent kernel exploitation. So truncation was not an option. That being said, maybe you can use actually an indirect bug, like we saw with the memory reads. Maybe I could overwrite or truncate some kind of variable, which is not quite a function pointer, but that is going to be used later on, for instance, as the length in a memcopy and trigger, for instance, secondary stack overflow, which was not supposed to be there. If you're using global data to make this memcopy, if you're using global data, it's pretty likely that you can overwrite this global variable. If you have to target the stack, not really. But if it's global stuff, it's pretty likely. So that's the plan B. We're gonna look for normal variables that we could overwrite or truncate and try to trigger a secondary bug. So the trick is to, in general, if I take Opera with its huge heap, especially if you need to do some heap spray, etc., before triggering the bug, trying to overwrite sequentially gigabytes of heap is out of question. This is not going to be scalable. It's going to take for ages. It's going to take forever. So there is a trick by using the unaligned flag inside the eFlag registers. If we set it, every time the application is going to try to dereference a variable which is unaligned, it's going to send you a SIG trap, a SIG bus, sorry, which is signal 7. So let me show you how this works. We're going to trace into SSH, set this trap flag repeatedly, and try to list inside SSH all the unaligned memory reads and memory writes. If I can only write 0 to 4-byte aligned locations, what I want to do is actually overwrite one of those. Okay, so same thing as before. I'm starting a new SSH session. I find the PID of the newly created fork of SSH, and I attach PMCMA to this running process, specifying the unaligned flag, which is not the default analysis. So if I get back to the PMCMA screen, it's actually showing me here all the instructions which are using unaligned memory and printing me the state of the registers, which allows me to know from which location they're actually reading or writing to. Okay? If I have this case of being able to write only a constant value to 4-byte aligned stuff, what I'd like to do is spot a reading instruction here from an unaligned memory and truncate the destination, the source operand, the source memory address. If you pay attention here at the registers, this is actually a 64-bit version of SSH. Porting the tool to other architecture is just a matter of changing those few shellcodes we're using. So in this case to 64-bit assembly. If you want to port it to BSD and OSX tomorrow, what we need to do is exactly this. So port the few shellcodes which are architecture specific to OSX. That's what we're going to try to do tomorrow for the Hackaday session. Okay, one more thing. How do you defeat randomization? The best known example of this was at Consequest in 2010. It was demonstrated that if you have a string in JavaScript, basically the storage of a string in JavaScript is its length followed by the content. If you have somehow a heap overflow, you can overwrite the length of the string, and if you use it later on in your JavaScript, say the length was initially 10 and you put it to 100. So you're going to read the 10 bytes of your string, and then you're going to read 90 bytes of heap data which is following your string. If inside this leaked data there is a pointer to any of the sections, so like a function pointer for instance, you have a repeatable way to defeat randomization. You only need one function pointer to another section, because of the way randomization is performed in Linux. It's actually a translation of all the libraries. The libraries have a constant offset from each other, and they are not randomized like randomly, if I may say. Okay? So if you find a pointer to, say, a writable section or an executable section in the leaked bytes, you can know where is anything in memory. So the idea is, can we actually extend this methodology not just to use to work with applications who do not use JavaScript, for instance? Because JavaScript was a good idea, but if I want to attack SSH or Apache or whatever, I'm unlikely to be able to use a leakage in JavaScript. So the idea is to use ptrace syscall, which basically is going to send an event back to the debugger every time I'm doing a system call. Look at all the system call which allow a process to send information outside the process. So this can be like through sockets, through write, whether you write to the standard output or whatever, or file. And look at the data which is sent and how many bytes are sent. So we can record this. Then the idea is to use the make fork primitive we've been using to create many offsprings and overwrite a different location with dummy data. What you're using as data does not matter. What matters is that in this newly created fork, you also use ptrace syscall, and you monitor the differences between the original process and the newly created process. If the size of what you're writing is different, or if the content is different, you may have found, you have found a way to get an ASLR leak. If you take the write write syscall, for instance, there may be two ways to get this. Either you change the size of the write, so say the normal application was supposed to write 10 bytes. If you manage to overwrite global data and you actually change the size of this write to 100, you get 90 bytes of leakage, which may be enough to get a pointer to another location and deduce the whole mapping of the binary. Or you may be able to change not the size, but like the start, when it starts to read. And if instead of reading from a given location on the heap, you can make it read from any location you want inside the binary, you equally win. So this is not yet implemented fully inside PMCMA, but we're working on it. This is a really cool, I think this is a really cool feature to get, honestly. Okay. So we have seen that we can automate the reverse engineering of finding function pointers and stuff. Actually, PMCMA is also currently capable of finding you calls to calls tables and things like offset plus a register. So if the returning address is not exactly F1, F2, F3, F4, but something a bit bigger or a bit smaller, it may be because it's using a offset plus, base address plus offset address. Okay, I'm a bit late, so I think we're gonna just do one more thing. Sometimes inside a process, you won't be able to find a writable function pointer directly because of randomization. If I find a function pointer, if I find a function pointer, but it's in a zone which is heavily randomized, the odds of me to manage to overwrite it are very low. So what I can do is try to find in a less randomized section. We saw, for instance, that in SU or sudo, the main process is not randomized, only the shared libraries are. So if I have a function pointer in a shared library, but it's, say, inside a complex structure, inside a data section of a shared library, evenly randomized. But if I have a function if I have a pointer to this section inside the shared library from a less randomized section, what may be good to hijack is the pointer to the structure containing the function pointer and not the function pointer directly. And this is a nice way to bypass ASLR. So we have extended actually PMCMA to be able to do also this kind of analysis. All right, I think I'm going to stop here. Do you have any question?
Thank you very much.
No worries. If you'd like to download the tool, so there again it's on pmcma.org, and we're welcoming patches and forks, and even if you don't submit it to me, at least use it and enjoy.
Thank you very much, Jonathan.
Thank you.